Hey guys, this is Mr. T again. This is another video. This one is again on linear programming and the Simplex algorithm. It's a little extra one because I do realize this topic, this concept can be a bit difficult. It's new for some people. And yeah, I wanted to chuck together a shorter video than the one that was in 3 parts. It lasted half an hour. The last one that may help you just get your head around this stuff. So this is another shorter worked example video of a linear program question. I want you to spend some extra time instead of trying to just understand the whole process while I'm doing a really difficult question, to observe the steps I'm taking to complete the question. So the first is to define all the constraints and draw them accurately, especially if it's a word question. 2, shade the feasible region, the simplex, according to the constraint inequalities. So you'll know what direction to colour above or below the lines based on the inequalities. 3, identify all the feasible solutions, dot them out in the simplex. These are the whole number grid locations on the boundary of the simplex, on the simplex vertices, the corners, and within the simplex itself. And you're only been able to do that if you draw the simplex very accurately. Number 4, you need to define the objective function. You need to know what you're minimizing and maximizing. Number 5, create a table of all the feasible solutions on the left side of the table and results of the objective function on the right side of the table. Step 6, identify the optimal value, the min or the max, from the table once you've found the results of the objective function with all the feasible solutions. Then number 7, answer the original question in sentence form. So this example here is a bit simpler. We don't need to use a word question and define the simplex based on that. We're pretty much given the constraints straight out. So our constraints are x is greater than or equal to 0, y is greater than or equal to 0, so 2 of our constraints are already there, the x and the y axis. Another constraint is 2x plus 3y is less than or equal to 18, and 4x plus 3y is less than or equal to 24. Find the maximum value of the function 5x plus 4y, so we're given the objective function this time, 5x plus 4y, and state the value of x and y where this maximum occurs. So we need to find where the maximum value of this function occurs within this simplex and state the location of that, and state the maximum itself. So you need to start by drawing the axes, x and y axes, and a plastic ruler on a glass screen. Not the best, but we'll manage. So try and draw as accurate as possible. Across here. Now, I'm not going to decide on the scale just yet, because I need to know where the intercepts occur. I know where the intercepts for x is greater than or equal to 0 and y is greater than or equal to 0. They're just the axes. But what about 2x plus 3y is less than or equal to 18? So 2x plus 3y is less than or equal to 18. I want to know what the intercepts are. So x int is going to be when y is equal to 0. 2x plus 3 lots of 0 is equal to 18. 2x is equal to 18. X is equal to 9. The y-intercept, 2 lots of 0 plus 3y is equal to 18. 3y is equal to 18. Y is equal to 6. Looking at the other one, 4x plus 3y less than or equal to 24. The x-intercept, 4x plus 3 lots of 0 equals 24. 4x is equal to 24. X is going to be 24 divided by 4, 6. Y-intercept, 4 lots of 0 plus 3y is equal to 24. 3y is equal to 24. Y is equal to 24 divided by 3 is 8. Alright, so we have what the information we need for drawing the simplex. X is greater than or equal to 0, so our first simplex, our first boundary is along the x-axis. Our other boundary is along the y-axis, so I'm not going to bother drawing those. Now, x is equal to 9. I don't want to crowd it up on the bottom left of the thing, so I'm going to go 2 at a time. 4, 5, 6, 7, 8, 9 on a spacious graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so x crossing is at 9, y crossing is at 6. So that's our first boundary line. Need to draw it accurately. So this one was 2x plus 3y is equal to 18. The inequality comes in when we're trying to colour it in. It's going to be less than, so I'm going to colour it under that line. But I needed to get the other boundary of the simplex as well. X is equal to 6. Y is equal to 8. So that's the other boundary line. That one is the 4x plus 3y equals 24 line. So now we can colour it in because we know that this line is the y is equal to 0. And this one is the x is equal to 0 line. And our constraints are x is greater than or equal to 0, y is greater than or equal to 0, and we're 2x plus 3y is less than 18, and 4x plus 3y is less than 24. So we're going to colour in underneath these lines here. Now just remember that our grid lines are every 2. So I've coloured in red the feasible region. Our feasible solutions are every whole grid line, but the grid lines are every 2 squares on this grid. One there, and all these edge ones too. And the corners. Oh, there's another one there. That's it. That's it. So the simplex to run the simplex algorithm, we need to chuck in the feasible solutions and the objective function on this side, which was 5x plus 4y. Okay, however, you can see that we have a ridiculous number of points here. We have a ridiculous number of feasible solutions to run. That would be ridiculous to ask you to do that in an assessment task. Now, what we proved in the previous question was that the optimal value of a linear expression, the optimal value, occurs at the vertex of a simplex. So we only need to run the feasible solutions of the vertices. So that, and that. We don't need to run all the other ones because we know they're not going to be the optimal value for this function, because the maths shows us that the optimal value of the function is going to happen at one of the corners of the feasible region. This would be a waste of time to find all of those. So that saves us a lot of heartache. This first corner is 0, 6. Bottom corner, 0, 0. This middle corner, 3, 4. Bottom right corner, 6, 0. So, save us a lot of time. We don't need to do all of those feasible solutions. 0, 0, 0, 6, 3, 4, 6, 0. So, to work out the answer to the objective function, 5 lots of 0 plus 4 lots of 0 is going to be 0. 5 lots of 0 plus 4 lots of 6 is going to be 24. 5 lots of 3 plus 4 lots of 4 is going to be 15 plus 16. 25 to 6, 20, 31. 5 lots of 6 plus 4 lots of 0, 30. And we were trying to find the maximum value, therefore the maximum value occurs at 3, 4, which is 31. Therefore, max value of 5x plus 4y is 31, occurring at 3, 4. Now, while I have some time on this video, because it's not going to be have to be split into multiple parts, I just want to show you how this relates to the fact that this function is a line. 5x plus 4y is equal to 31 is a line of itself. If we draw it, 5x, the x int, 5x plus 4 lots of 0 is equal to 31. 5x is equal to 31. X is equal to 31 divided by 5 is not going to be a nice number. 31 divided by 5, 6.2. Y int, 5 lots of 0 plus 4y is equal to 31. 4y is equal to 31. Y is equal to 31 divided by 4. 7.75. This line, defined by those intercepts, so 6.2 is going to be sort of there, and 7.75 going to be halfway between 7.5 and 8. That line should just touch the optimal result that we defined in the answer to that question. And it looks like it does if I can draw it accurately enough. There you go. So this red line, 5x plus 4y is equal to 31, is a diagonal line going across, and it just touches, it just kisses the edge of that simplex, and that's why that's the optimal value, because that's the highest value they can be that still falls under the boundary of this simplex. If we moved it across at all, it's not going to touch the simplex. It's not going to meet the constraints. If we move it inside the simplex, well, it's not going to be the highest value anymore of 31. Alright, so that's just relating back what this objective function is. What is it? It's actually a line. 5x plus 4y can be any line of this slope. It's scanning across. It's scanning all the way across. But the optimal solution only occurs when it touches exactly that corner of the simplex, and that's the highest value it can be. Because if you had this diagonal line and you had it scanned under there, well, okay, those are possible solutions, but they're not going to be the highest. They're not going to be the maximum value that 5x plus 4y can be. The maximum value that 5x plus 4y can be only happens at this very corner here, when x is equal to 3 and y is equal to 4. Alright, so hopefully that clears up some stuff, because this is a difficult topic. It's a little difficult to get around your head, and there's a lot of steps to it. Hopefully that helps you out, and I'll see you on the next video.